Hi, good afternoon, everyone. So welcome back to our free Asian math lectures. So last time we talked about some word problems. In particular, we discussed some classic category of word problem where you have two quantities. You need to figure out those quantities based on certain relationships among them. In particular, there are usually three particular relationships that are important. They are the sum and the difference and the multiplicity relationship between the two numbers. Because if we have two unknowns, in general, we need to know two conditions in order to figure out those unknowns. That you will learn later in algebra. But in terms of arithmetical methods, that translates into the situation where for the three relationships, the sum, the difference, and the multiplicity, if you know two of them, then you will be able to figure out those two numbers are. Therefore, in general, there are three categories of those problems. First, if you know the sum and the difference. Second, if you know the sum and the multiplicity, you can figure out the numbers. And finally, if you know the difference and the multiplicity, you can figure out the problems. So this is such a very important type of problems. I decided to give you a lot of homework problems. In particular, I actually gave you three sets of exercises, number 6, 7, and 8, and they become increasingly more difficult, particularly the last set, exercise number 8, contains quite some difficult problems. So to not overwhelm you, I decided for this week's lecture, which we will review and revisit place values and the vertical addition algorithm, I will not give you actual homeworks. I may give you some exercises later on, but not for this week. So for this week, you should continue to try to solve those 30 word problems that essentially for lecture 6 last time. So today we will go back to reviewing what you probably had already learned earlier. So that is, we review what natural numbers mean, then define addition. And then we discuss commutative and associative laws. Earlier on, there was quite kind of just a challenging question, say, when we define addition, we say that that's a repeated counting. And if I give you a very just difficult addition problem, let's just say two large numbers to add, how do we do it? Shall we just count those two numbers together? Or there's any way we can make it much faster? Otherwise, if we cannot just handle that situation, essentially addition, while sounds good, it's essentially a redefinition or restatement of counting. Even we have defined addition as an operation, if every time you perform addition, you have to actually count, then it's not really that helpful. And today we answer that question. And to do that, we first need to study the place values and the decimal system, which I'm sure everybody has known and has studied. But it would be very impressive if you truly understand and appreciate how excellent and how brilliant this system is. So today we're gonna take a look at that. So we said that all mathematics starts with counting. In particular, starts with natural numbers, because that's how we do anything about the math in our life. The first time we need to count the things, right? 1, 2, 3, 4, and of course we started at 0. But did anybody ever think about this question? If the number becomes really large, how do we represent such numbers? Well, of course, you have know we use digits. That is from 0 to 9 to represent any large numbers. And this is so-called a Hindu-Arabic system or Hindu-Arabic positional system. We'll see what that means. But essentially, think about, let's just say 3,872. This is a very large number, right? At least for young kids, this is a fairly large number. But this can easily go even larger. So we just keep adding additional digits to this number. So how many thousand, million? So this is 72,783,872. It's a huge number. Before you take this for granted, let's go back to history to see what if we did not have this Arabic Hindu system. By the way, I ask you to watch a few, I think, well-select YouTube videos on just base systems and the positional number systems. If you watch them, today's lecture probably will be a little bit easier. But if you have not, I still urge you to watch those videos just to help you just acquire a really deep understanding of how important the Arabic Hindu numeral system is in the history of math, and by extension, in the history of mankind. Because without math, you will not have the modern life, the nice life you are enjoying today. You have to go back to 1,000 years ago, and apparently that's not something desirable, at least to most people. So let's think about the need of a positional numeral system to count. Well, we count, that number can go to very large, right? We just saw how big that is. But before those positional number systems were invented, people will have to assign a symbol to each such number, right? That was the very beginning, but that quickly you will run out of symbols because you just cannot have that many symbols for each number. Each number will require a unique symbol for it. By the way, if you read the reading materials, we say that the choice of rows 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, they're nothing but symbols. Okay? You can easily replace anyone with an arbitrary symbol like this, or whatever you want, just random things. They're nothing but symbols. They look so nice today only because we get used to it. Okay? They're just symbols. So, if we have very large numbers, apparently quickly we will run out of symbols. At some point, we will have to think about, can we reuse the same set of symbols to represent very large numbers, and ideally arbitrarily large numbers? Well, you think the Hindu-Arabic system looks so simple and so easy, and you took it for granted, but that was definitely not the case in history. Before this was invented, people across the world use all kinds of systems to denote numbers. And some of them were kind of similar to the Hindu-Arabic system, but some of them look very different, and to be perfectly honest, very bad. Okay? And perhaps the most well-known and still kind of current, that means that still living, not dead, system is the Roman numeral system. And that system is really an example of very poor ideas. Well, I'm not trying to just kind of badmouth that system from today's perspective, because at one point it was still kind of advanced and very helpful, at least compared to the most primitive, human life, right? So it exists for a good reason. It did not came from nowhere and serve no purpose. So how does the Roman numeral system work? Well, let's take a look. So the numbers in this system essentially by combination of letters from the Latin alphabet. Okay, I don't know Latin, but I do know those some of those alphabet. Okay, so generally you have the following. Well, and this is only limited to up to thousands. And in Roman number system, when you go to 1,000, 2,000, that's considered a very large number already. So unimaginable from today's perspective, right? So how does that work? Well, they have some predefined, prepackaged numbers. So the symbols here, they define certain numbers with particular symbols. Like a 1 is 1, like I, right? I can only say it in English, right? Not Latin. So this I is 1. And if you have 5, that's a V. If it's a 10, it's an X. And similarly, you have 50, 100, 500, 1,000. Those symbols, think about it, those symbols have a one-to-one mapping to those numbers, 1, 5, 10, 50, 100, 500, 1,000. It's a one-to-one mapping. This may sound ridiculous from today's point of view, right? We only need 9 digits. Why you have this kind of thing? Well, that's again because you have taken everything that was historically brilliant for granted. It was a huge milestone in human history, the Arabic numerical system. But today it looks so simple. You cannot appreciate its brilliance unless you also study something like a Roman numeral system. So we have those symbols, right? Based on those symbols, they further define certain, essentially, arithmetical operations to get additional numbers. And those are kind of next level building blocks. For example, let's take a look at units. So we have already 10 is X. So, and I is 1. So anything between 1 and 10, how do we do it? Well, this is how to do it. They combine those symbols in a certain way, right? 1, 2, 3. You have 1, 2, 3, I, meaning 3 ones. That's just kind of using just a stick for tallying, right? 1, 2, 3. Some kind of just a intuitive, but very inefficient. You quickly see that you cannot continue this if you say have a large number 10. Did you put 10 eyes together? Your eyes cannot even tell the difference. So they decided that that's why they have from 1, they have the next stop at 5. So because the availability of 5, they decided that combine 1 and 5 to generate 4. Essentially, we know 5 subtracting 1 is 4. So they put I or 1 to the left of the 5. That means that you need to do a subtraction, subtracting the smaller one from the larger one. So you get a 4. So then next one you have 5. How about 6? 6 now is 5 plus 1. So in order to distinguish this from 4, which is subtraction, they put 1 on the right of 5. So this left-right relationship tells whether you should perform subtraction or addition. So now we know subtraction is 4, but 6 is 5 plus 1. Then you can continue to do this for with 2 1s, 3 1s, so that you get 6, 7, 8 like this. Okay? At this point, you probably feel this is already doesn't sound very smart, but it was smart at that time. 9. 9, because now it's much closer to 10 rather than 5, they decided to put a 9 in this way, put 1 on the left of 10. Well, at this time, you can think that we can do 8 in a similar way. We put 2, 1 on the left of 10 to get 8. Yes, in theory, that is possible, but this is a kind of hard-coded rule, so they decide not to do that. So A is written as 3 1s on the right of 5, and the 9 is 1 on the left of 10. So you don't have something like a 2 on the left of 10 to get an 8. Okay, so far, that's, you already see that just to represent from 1 to 9, it's that difficult under this system. So you will see that additional ones. Now they extend this idea to additional just kind of poles. So for 10, we already have this 1x. So 2x, 3x give you 20, 30, and then here comes this 40, right? Next predefined symbol is 50. So by the same idea, you put 10 on the left of 50, you get 40. So then comes 40. And then you use the same idea, you put 10 on the right of 50 to get 60, 70, 80. Once again, you at the next 90, you put a 10 to the left of the yet next big number, which is 100 here, which is C. So they put 10, which is X, to the left of C, which is 100, to get 90. So you can see the idea how they define numbers in such a hard-coded way. And 100 is the same thing, because the next one is 500 and 1,000. So you can see 2C, which is 100, 3C, then C to the left of D, which is 500, and so on. At this point, probably you feel your brain really needs to be high-powered. Perhaps just like the latest AMD CPU in order to do this kind of conversion in your mind, right? But this is not the actual story, because those are just the main big numbers or nice numbers like 10, 20, 30, 300, 500. What if you need to represent an actual number like 328 and so on? Well, that's where things get even more interesting, right? So take a look. Now, this is how numbers are actually represented in the Roman numeral system. Let's have a look. 39. The quickest way to get 39 is you first get 30, then get a 9, right? So because 30 and the 9 were already defined in this symbol table, so 39 is represented as XXXIX. Impressed already? Well, how about 246? Well, the quickest way to get 246 is you get a 200, a 40, and then 6. And they are all available from this reference table here. So 246 is written as CCXLVL. Oh, VI, I'm sorry. Incredible, right? How about 2,421? Well, you have 2M, here's M is 1,000. Then CD, that's 400 right here. Then 20 here, and finally 1. So it represents MMCDXXI. Are you already just kind of totally lost? I guess I am. I have no idea how to track this system. And this is just mere representation. If you do any arithmetical operation like addition, subtraction, you can imagine how difficult this would be because the system is already so complicated. Developing some good way to perform those arithmetic operations would be even more challenging, right? You can just imagine that. I actually don't know how to do that, but you can imagine it will be extraordinarily difficult. And this represents the most advanced civilization for a long, long time. Okay, so actually this system was in actual use until the late, I think it's around 1300 to 1500. So the the Hindu Arabic numbers were just introduced into Europe much later than its invention, which was around, I think, the 8th century, sometime around that. So don't laugh at this system, but these are already at its time the most advanced math. Okay? So, just for the reference, this is a chart of the Roman numerals just from 1 to 100. Who can just memorize all those things? Well, people had to at that time. So, now you are convinced this is a very poor system, right? Especially if you want to do anything meaningful from today's perspective, like addition, subtraction. We haven't talked about multiplication and division, but this certainly is painful. Okay, without that in mind, you won't be able to see how beautiful and brilliant the Hindu Arabic numeral system is. So, first of all, it's a system called positional numeral system, and in particular in base 10. What does that mean? Well, we already saw earlier. Let's just say, let's have our example. Let's just say 6,835. It's called a positional number system because here, while we have 4 digits, each of them represents a different position in the place value system. So a position is also called place. So the very first one from the right, it's called unit place, right? We all know that. And this can only be from 0 to 9. And the next one, it's called tens place. This is unit place. The next one is the tens place. But once again, this can only be from 0 to 9 and so on. You already know that, I'm sure. So you have hundreds place and thousands place. And each time you only need from 0 to 9. So this is called a positional system because each digit has a position and holds a place value. In other words, each of the 5, we have 5, represent the basic unit digits. So if this is 2, it represents 2. But for the next one, the tens place, because it's tens place, each digit here represents that digit times 10. So 3 in the tens place really represents 30. Okay? So the first one is 5. The tens place represents 30. And of course, you know the hundred place represents 800. Why? This is equals to 8 times 10 times 10 again. And of course, 30 is 3 times 10. And the 5, what is 5? 5 is just 5 times 1. And for those of you who are really advanced, you probably have heard this can be written as 10 to the second power. This is 10 to the first power. And what is 1? 1 is actually, we artificially define it as 10 to the 0 power. Anything to the 0 power, any positive integer to the 0 power is 1. So that's just we will study this later, but just a side note. And finally, the last one, the highest place value represents 6,000. So this 6 times 10 times 10 times 10 and times 10. So you can see that each time you have a higher digit, the place value it holds is 10 times higher than the previous digit in the lower place value. So why this system is so brilliant? Well, you have to think about two things. First, it only uses a relatively very small number of symbols, right? 10 in particular. And don't forget 0. 0 is an important part. It's a huge part. Because we have this positional system, each time if you say you run out of numbers or symbols in one place value, what do? You have a carry to the next higher place value digit. So let's just say if you count 1, 2, 3, 4, 9, when you reach 9 in the unit place, the next one would be 10. 10 now, we don't need an actual symbol for 10. We simply carry that 10 to the higher place value. Now, because this place value is already 10, for our unit place 10 to be represented in this higher place value digit, we bring it down to 1. And that's why we have 10 here. So in other words, if once you have 10, you just get rid of that 10 factor divided by 10 to go to the original unit digit that is from 0 to 9. So if nothing in that place, this would be 0. Now you have 1, you just carry 1 to the 10th place. So carrying naturally happens. Okay? So this is not just the only benefit of a positional number system. Okay, we'll see shortly what that means. So the key idea here is that you can combine a limited set of symbols together with position values or place values. That's why we call this a positional numeral system. Each digit has a particular position within the representation. So we can do this continually to any digits we want. So in theory, we can do arbitrarily large numbers. Okay? But of course, if the number is really large, then you may need many digits. But it's not that bad. It's a very good balance. So this particular number we choose what we call base, which is 10. Base means that how many digits you need as the basic set. In this case, we need 10. So this is called base 10 system or base 10 numeral system. Another name is decimal. Decimal essentially, I think this is also from Latin. Correct me if I'm wrong, but that's something related to 10. Okay, so this is a decimal system. We will see today why this number 10 historically seems to be somehow a little bit random, but of course it has its justifications. But it's also effectively, from a practical point of view, it's a very well chosen balanced number. So what if this number is not base 10? We'll see that. And this fact that 10 is a good choice will be evident in all the vertical arithmetic algorithms. So we promise we will study one today, that is addition, but you will see the same thing in multiplication as well. And because subtraction is the inverse of addition, division is the inverse of multiplication, so that also applies to subtraction and division. 10 is a good choice. Okay, so before we continue to discuss, you may want to think about what if the base is not base 10? Well, in history, the Hindu Arabic system was not the only positional system people in the world came up with, and was not the earliest either. So Babylonians actually, way before the Hindu Arabic system, they invent something called base 60. So you can see that how difficult this is to represent their numbers. They have 60 different symbols, and they all look kind of similar, but they are different. So this is how they use the 60 symbols in their base 60 numeral systems. Actually, 60 did not just happen randomly. 60 is actually a good number because it has a lot of divisors, right? We actually still use this system at a few places. For example, we have 1 hour, that's 60 minutes. Every minute is 60 seconds. That's actually a base 60 system. We also have base 12. So you can see that here, this is kind of just a theory. People devise this base 12 system by using their fingers. Each finger except the thumb, each finger has 3 knots. So they use that 3 times 4 equals 12. That's how you use this to count, rather than our decimal system where we have 10 fingers. We can count 1, 2, 3, and so on. They use this to count 12. But 12 is actually also a good number in the sense that it's not that big. It's just 2 bigger than 10, but it has more divisors than 10, right? Much more. You have 2, 3, 4, 6, and of course plus 12 itself. So, but 10, you only have 2 and 5 if you exclude 1 and 10. So that means that when you try to divide something equally, the base 12 system has a lot of advantage. So what is 1/3 of a pi? What is 1/3 of just your time? If say you have certain number there. So 12 is a pretty good choice. So that's why some people even debate today, maybe we should use base 10, base 12 rather than the decimal system. That's not a totally ridiculous point. It actually has its just upsides. So super importantly, you will learn in modern society, you also have the binary system, which only has 2 symbols, 0 and 1. This is widely used in computer. I guess everybody is a computer fan, right? If you are not, you are a video game fan, are you? So it's very important to understand that computers, at least of today, maybe we'll have a quantum computer in the future, but for today, all the computers deep down there, they use the base 2 system, which can be converted to something like a base 8 or base 16, but fundamentally, it's base 2. All the numbers consist of only 2 symbols, 0 or 1. And why is that? Because in the real physical hardware that made the computer work, we use transistors, all those circuits. And transistor, to build such things, it will be the easiest if you only have 2 states, right? Either on or off. And that's exactly what a transistor does. It's based on 2 states, certain semiconductor states. If something is on or off. But because of that, it's very easy to design circuit. If you have more than 2 states or 3 states, things will become much more difficult. Because if you only have 2 states, you only need to make all the logic just determination is this on or off? Is this gate on or off? So that way, the logic, the circuit design can become much easier. So it's still very complicated, but it's already at the easiest. So that's why we have the base 2 system, which we will discuss in this class this year a little bit later when we study number theory. So you have all those base systems, and each of them has some good things and some bad things. For example, the binary system 0101, that's very easy to implement in physics, to build a computer, but it's really just inconvenient. Even a relatively small number, you have a lot of digits, and we will see that the information there is not so well organized in the sense that we human beings can quickly do counting. Computers will feel very happy about this, but certainly not a human being, okay? So we have to understand positional numbers. This is the second best thing I just mentioned. Positional numbers, they're pre-packed with very rich information. What do we mean by that? Packed with very rich information. So this is the second important point that you want to understand positional numbers, particularly base 10. Firstly, they only use a limited number of symbols. That's good. We don't want to have too many symbols, like the Babylonian base 60s numeral system. But all the positional numbers are pre-packed with rich information. What do you mean by that? Well, you can think about when you are given a number, let's just say 34. In the Babylonian base 60 system, the concept of 34 is nothing but some weird symbol, right? I just draw randomly. It's a symbol. That symbol represents 34. Other than that, it does not have any actual information. But if you use the decimal system to represent it, you have 2 digits, 34. And that is not accidental. You can consider that this many things, 34, if you do counting, has been somehow pre-sorted, pre-processed, and now pre-packed into this nice form, 3 and 4. Of course, 3 is the tens place and 4 is the unit place. Why this is significant? Consider this example. If you have to count a pile of cash, let's just say your mom gave you some cash reward. Well, she did not tell you how much money she actually gave you, just handed you some cash. You get some 2 choices. One is that your mom, for whatever reason, decided to give you all $1 bills. Okay? And she did not tell you how much money you got. How do you figure out how much money you actually got? You count it, right? 1, 2, 3, 4. And because every bill is a $1 bill, you really have to count each one of them in a way very tedious. Because $34 will equal to 34 $1 bill. But on the other hand, if your mom just do what she should do, just give you some notes that have different face values. So, for example, 34, what will she do? Give you 3 tens bills and then 4 $1 bills, right? How now can you count it? Much easier. You count 3 tens bills, 1, 2, 3, and then 4 $1 bills, 1, 2, 3, 4. Then you know you got $34. This looks Did anybody actually think about this? What happened? Because the bills have been organized in a way that makes counting very easy. So 3/10 bills, that somehow we group those 30 $1 bill into 3 groups. Each group is a $10 bill. And the remaining sounds like a residual $4 in just $1 bills. That's okay. We have to, at some point, we cannot get around that. But those $30 have been just presented in only 3/10 bill. That's a brilliant idea from a counting perspective, right? Because each $10 bill represents some pre-packed information for you. It has already been counted and organized for you. Hey, this is just $10. You don't have to count 10 of them. I give you just one bill and you know it's 10. And I give you 3, you know it's 30. And so together you have $34. That's actually very important property of any positional systems. So like Babylonian, well, if they do have multiple place values, I'm sure they probably should have, but each position has the same pre-packed information. If it's Babylonian is base 60, so let's just say if it's 34, this 4 is actually 4 in the Babylonian base 60, and the 3 is also the next higher place value. But what does 3 represent? 3 represent 3 times 60. Okay, that's 180. But for a number like just 34 and such a symbol, it's a true decimal 34 because it's smaller than 60. It has no such organized information. It's just a hard-coded symbol. Okay, so that's the difference between, a hard-coded symbol and a positional number which has pre-packed information there. And you will see this is important. So now we answer our earlier question, how do we do addition without actual counting? For that, let's have a quick review of how we define addition, right? So let's revisit this problem. We have 5 apples, 3 bananas. We have already counted there are 5 apples and 3 bananas. How do we figure out the total? Well, without any advanced thing to do, you count them together. Also, you don't have to count starting from 0. You start from 5 because you know you have 5 apples. Then count 6, 7, 8 to get 8. That's the total, right? So that means that addition is defined just as repeated counting. All right? Essentially, 5 increment 1, the increment 1, and increment 1. 3 times gives you 8. That's the meaning of 5 plus 3. And on the number line, with this visual aid, you can see that you're starting at 5. That's what you have already known. You have already counted there are 5 apples. From that point, you counted the bananas. 1, 2, 3, and you reach at 8. That's what happened on the number line. So we promise that if this is just addition, simply a redefinition or restatement of the counting, why we want it? It doesn't help in any way, right? For example, if we want to perform this number, what is the number of 876 plus 948? Well, under this definition of a counting, this addition, you have to perform the actual counting. Find 876 on the number line, continue to count 948 times, which I'm sure nobody wants to do, right? If you want to do it, it's more likely than not you will make a mistake at some point and get incorrect counting. So we promise that addition enables accelerated counting. Why? And how? Well, that's because we have the equally brilliant vertical addition algorithm. Everybody knows how to do this, right? You learned this maybe in grade 2 or 3. Excuse me. You line them up vertically, 876, 948. You first do the unit place addition. 6 plus 8, you have a carry. So 876, 948. 6 plus 8, you get 14. You have a carry here. 7 plus 4, that's 11. Plus another 1 from the carry, that's 12. So you get another 1. Then you get a further carry to the hundredth place because you have 12 in the 10th place. 8 plus 9, that's 17. Plus 1, that's 18. So finally, you get this. So in this way, we don't have to actually count 948 cases. But why this algorithm works? Well, did you ever ask this question to yourself? Why this algorithm works? How do we know this result, which essentially is going through this vertical addition algorithm? It's a procedure. It's an algorithm, what we call in computer science algorithm. How do we know so performed this result, 1824, is exactly what we should get if we do the actual counting on the number line or through that definition of natural numbers. Remember, we have a kind of continued, essentially recursive definition of counting numbers or natural numbers. How do we know this is actually correct? Well, you were taught by your teachers, this is correct, this is the way, but why? This is a very deep mathematical question, and without understanding things like this, your math becomes so boring and so kind of frustrating because you need to memorize a lot of things without truly understanding why it worked, why those things are true. Okay, so we'll take a look of why this works. That's why we study commutative and associative laws, right? In homework number 5, at the very end, you were given some very challenging problems, essentially ask you to show a theorem that is based on the commutative and associative laws. And that theorem is so powerful, it's so general, right? It says that for any collection of natural numbers, adding them, no matter how many numbers I have, 5, 6, 7, doesn't matter, 200, when you add those numbers up, it doesn't matter in what order you perform the addition. Any order you choose, you can use parentheses to make the order really complicated, not just even a linear order 1, 2, 3, 4. After some shuffling, or we call permutation, not just even that, even within the same permutation, you can use layers and layers, parentheses to make things very complicated. But this theorem says that it doesn't matter. For any such order, you will get exactly the same result. And we took pain try to give you a more rigorous proof in the homework solution. Do read it if you really just want to understand this very deeply, very well. Okay, so this theorem is essentially the summarization of how you can use commutative law and associative law repeatedly and in a very complicated way. So this is replace both the commutative and associative laws in the sense that it's based on those two laws, and the two laws are just special case for this theorem, but this theorem gives you unlimited just way to do whatever order you want to do in terms of performing addition. Okay, so in particular, we can do this addition this way, right? You can break down 876 into 800 plus 70 plus 6, and similarly 948, 900 plus 40 plus 8. Why this is true? Well, essentially because we know if we add 800 add 670 add 6 equals to 876. That's because of the fundamental nature of the decimal positional system. 800 means that you have a digit A in the hundredth place. 70, you have a 7 in the 10th place, and so on. So we know this is just nothing but the very basic definition of how the decimal positional system should work. So then, once we get here, we can see that we can regroup them in a way that we group all the hundreds numbers together. We want to group 800 plus 900 and 70 plus 40, 8 plus 6. This is nothing but essentially commutative law and associative laws allow us to rewrite the original problem in such a way. Right? Once we understand this, we know that we can do 800 and 900 together. Then you can understand why this vertical addition algorithm works. To perform this, we do A plus 6. That's the unit place. That's exactly what we did the first time. Right? If there's an overflow, meaning the result is greater than 10, then that will generate a carry, which is a 10 part, which will goes to the next higher place value digit, which is 10th place. We understand that. And the remaining is 4. It stays in its current place value position. Okay, it stays in the unit place. Okay, so that means that here, the x plus 6 give us a 14. That means that 1, 4 remaining in its current place value, place position, and the 1 goes to the next higher one, which is carrying. And then for the same procedure, we calculate 70 plus 40, but because they're in the 10th place position, we only do 7 and 4 together. Effectively, we were doing 70 plus 40, right? It's just hidden there, but you don't need to see that. All you see is at this time, at this stage of the algorithm, you just perform 7 plus 4. Essentially 70 plus 40, but you pretend it only single digit to single digit addition, because the 0 there were completely hidden to you, okay? And don't forget that was a carrying from the unit place. So after performing 7 and 4, you need to do 1, then you get 12. And the same logic continues. You have a further carrying to the 100th place. So the next time when you do A plus 9, effectively you were doing 800 plus 900, but with those two zeros hidden from you. And of course, this time it also has a carry, so there's a 1 right there. And finally, you get to a carry to the 1000th place. So the very reason the vertical addition algorithm works is because the commutative and associative laws tell us that it must be the same result if we do it this way. Okay, so that's very significant because when we do 800 plus 900, also the number themselves are very big. Because of the positional system we so chose, we know we can ignore the hundreds to 0 part, pretend this is actually a single digit to single digit, namely A plus 9 operation. Well, fundamentally, it's actually 800 plus 900. And this is truly, truly brilliant. Okay? So, we actually show why this system should work. But along the way, let's just summarize the essence of this. when we do this vertical multiplication, we transform the original problem by the associative and commutative laws, regrouping those things into different components. And each component represents, say, hundredths place addition, tenths place addition, and unit place addition. But nominally, they are hundredths place. But practically, each one of those three is a single digit to single digit operation. Okay? So, what are the essence of all vertical arithmetical algorithm? Not just addition, because we'll see for multiplication later, pretty much the same thing. Well, you have to realize there are two things. First, the input information has already been pre-sorted and organized for you, right? You look at those numbers, that's what we said earlier. When you look at 876, it's, 876, it's such a well-organized, well-packed number for you. Already the major part of 800 already for you, 70 already for you, and 6 already for you. But if you think about it, the Roman system actually did similar things. That's why the Roman numeral system was not that bad. At least it was a well-thought, well-designed system that actually worked. It just, as compared to the Hindu-Arabic system, it has a lot of just defects. Okay? So first thing, the input has already been organized for you. That's why you can actually perform the vertical algorithm. Because if the information was not organized, just think about that counting money example. If all you get is just $1 bill, I give you a pile of cash, and that means that there's no positional value. It's just a symbol, some random symbol like that. Hey, this is 34. Then it will become much harder. And actually, we will consider that at the end of today. So the input information has already been organized for you. But remarkably, the output will retain exactly the same organization, right? Remember, our output here is 1,824. That means that the input 876, 948, they have been nicely prepacked for you. But when you execute the algorithm, you did not break it down those well-organized structure. You don't destroy the information therein. You use it. You take advantage of it. But at the same time, you generate an output which has the same prepacked information. Now we know we have 1,000 here, 800 here, 20, and 4. So this is equally important, because if you destroy this, then you cannot reuse this 1,824 for other purposes. The information got distorted going through the vertical addition algorithm, then that's totally bad. Very, very undesirable. So the output information is also well organized for you. The second important just property of vertical, say in this case addition, is that with place values and carrying with those two things, you only need to memorize single digit arithmetic, because that's all you need to do. Every step of the way, the practical operation is always based on single digits. 800 plus 900 is practically treated as 8 plus 9. So all you need to memorize is single digit arithmetic. How easy is that? Think about it. This is truly, truly remarkable. But that also means that what you need to memorize, you do need to memorize something. That's why if you recall in the first homework problem, you receive some questions like, maybe the second, I think, I don't remember exactly, but probably the second, you were asked to review the old friend vertical addition and think about this problem. When you do that, perform that algorithm to get a result, every step of the way, what was memorized as a fact and what was figured out on the spot. If you have already memorized all the single digit additions, you don't need to invent anything on the fly. When you perform the vertical addition, let's just say 3 plus 8. What is that? 11. Why is it 11? You memorize it. You truly memorize that. It's not something, say, you can take a shortcut for those just ridiculous reform math. They think that you need to figure out why 3 plus 8 equals to 11. BS. It's a fact that you do need to memorize. You don't do anything like counting on the spot from 8, 9, 10, 10, 11. You don't, no, 8, 9, 10, 11. You don't do that. You simply don't do that on the fly. You just memorize 3 plus 8 is 11. Okay? Because without doing that, you cannot perform the vertical addition algorithm. Yeah, if you can choose not to do that, your addition will become extremely painful. Every time I don't remember what is 4 plus 5, I need to count with my fingers, starting from 4, 5, 6, 7, 8, 9. Oh, that's 9. BS, right? You have to memorize this triangle. This is a less well-known triangle. It's similar to the multiplication facts table. But even for addition, you do need to memorize each and every those facts. For example, what is 3 plus 8? It's 14. How many are there? Let's calculate how many are there. So this is the first one. The first row you have 9 facts. The next one you have 8 facts. The third one you have 3 facts. So the total number of facts, addition facts you need to memorize is 9 plus 8 plus 7 plus 1. And from the homework problem, you know there's a quick way to do this. This is 1 plus 9 plus 2 plus 8 plus 4 plus 6, and there's a 5, which has no pairing. So there are 4 such groups, so that's 45. So in total, you have to memorize 45 addition facts. Well, at this point in your study, you probably have done that, but you have to understand there's a difference between you do need to memorize this as a requirement for executing the vertical addition algorithm, or it's just something you happen to pick up. No, that's not true. You are demanded to memorize those things. Okay? Now imagine why we say the base 10 is a good choice. You can see that with 10 as the base, you do need to memorize something, but it's not that bad. Only 45 facts. Okay? Well, on the other hand, if you have a binary system, what will you do? You only need to memorize 1 fact. And it is trivial. What is that? It's 1 plus 1 equals 10. In binary, 1 plus 1 equal to 10 means 1, 0. I mean 10 in the sense of binary system. So that means that you only need to remember 1 plus 1 equals to this number. That's all you need to memorize for binary system. The rest is carry. So that's why a binary number could be huge. Even say 526 in decimal, you only need 3 digits. In decimal, you need 10 digits for that. I think 12 digits for that. Okay, anyway, so now just imagine what will happen if you perform this same addition, 876 plus 948 in the base 1000 positional numeral system. What does that mean? It means that in this system, you will have 1000 symbols. And both 876 plus 948, both of those are hard-coded. There's no positional value because they're the unit digits. They are both the unit digits if the number system is base 1000. And how do we know the result? It will be a fact, okay? This thing, oops, we already erased that, but that's okay. So I think it's 876 plus 948. 876 plus 948. Because in the hypothetical imaginary base 1000 system, both of those numbers are unit numbers, hard-coded with a symbol, and you have no idea of what this is. The only way to find it out is to count from that value, 876, you count 948 times. Of course, we are using the decimal terms, but it's in that imaginary system. You have to count that many times to get the result, which is, I think I forgot what it is. Yeah, 124. Yeah, to get this fact, and you have to memorize this fact. That's how horrible if the base becomes so large. You have to memorize this number for any addition like this if the two are quote-unquote unit digits in that system. That's why base 10 is such a good balance. Not just because we have 10 fingers, but also 10 effectively only requires you to memorize a relatively small number of facts. With that, you can perform vertical addition for arbitrarily large numbers. Okay, isn't that cool? I think it's pretty cool. Alright, that's how important the place value, the positional number system is, and how important, how brilliant the vertical addition algorithm works. It does not require you to do hard counting for anything beyond the single digit arithmetical operation. Anything beyond that can be done by this algorithm, but you do need to memorize 45 facts. I'll see you next time.